Have you ever wondered why perfectly engineered systems sometimes deliver less than perfect results? Imagine a sensor, a crucial component in many modern devices, tasked with converting a physical quantity into an electrical signal. We often expect a perfectly straight-line relationship between what it measures and what it outputs. But sometimes, it doesn't quite work that way. Nonlinearity in sensor output characteristics occurs when the electrical signal a sensor produces is not directly proportional to the physical quantity it is measuring across its full operating range. Instead of a consistent straight line, the response curve might bend or flatten, meaning a change in input doesn't always lead to a proportionally equal change in output. This deviation from an ideal linear response is a fundamental consideration in sensor design and application. The root causes of this nonlinearity are diverse and often inherent to the sensor's operating principles and materials. One primary reason stems from the intrinsic physical properties of the materials used in the sensor itself. For example, the resistance of a thermistor changes with temperature in a highly nonlinear, exponential manner, not a simple linear one. Similarly, Hall effect sensors, which measure magnetic fields, can exhibit nonlinear voltage outputs, especially at very high or very low field strengths due to saturation effects within their semiconductor material. Mechanical sensors, like strain gauges, might show nonlinearity because the material's elasticity is not perfectly constant under extreme stress, or due to geometric changes at large deformations. Another significant contributor to nonlinearity involves the transducer's operational limits and physical structure. Many sensors have a specific operating range beyond which they exhibit saturation, where further increases in input no longer yield a proportional output increase. Think of a microphone distorting at very loud volumes, its output reaching a maximum limit. Furthermore, phenomena like hysteresis, where the output for a given input depends on the previous input history, and whether the input was increasing or decreasing, also introduce nonlinear behavior. Even the signal conditioning circuitry designed to amplify or filter the sensor's raw output can introduce nonlinearity if not carefully designed, particularly with operational amplifiers operating near their power supply rails. Environmental factors such as temperature drift or long-term aging of sensor components can also exacerbate these nonlinear tendencies. Understanding these causes allows engineers to effectively mitigate their impact. One common approach is multi-point calibration, where the sensor is tested at numerous known input values across its range, rather than just to points, to map its actual output behavior. This data can then be used to create a lookup table or a polynomial transfer function that corrects the output. Digital linearization techniques involve algorithms applied in software to compensate for the sensor's nonlinear response, effectively transforming the raw, nonlinear output into a linear one. In some cases, analog linearization circuits can be designed using nonlinear components to counteract the sensor's nonlinearity before the signal is digitized. Additionally, carefully selecting a sensor whose most linear operating range matches the application's required measurement range is a crucial design consideration. Grasping the concept of a sensor's transfer function, which describes the mathematical relationship between input and output, becomes paramount when dealing with nonlinearity. It is not merely a theoretical deviation. Nonlinearity directly impacts measurement accuracy and system performance, especially in precision applications like medical devices or industrial control systems. Ignoring nonlinearity would lead to significant measurement errors and potentially unreliable system operation. Recognizing that most real-world sensors are not perfectly ideal is an insider detail that differentiates robust engineering from wishful thinking. Ultimately, understanding what causes nonlinearity in sensor output characteristics empowers engineers to make informed decisions about sensor selection, system design, and signal processing strategies. By accurately characterizing a sensor's nonlinear behavior and implementing appropriate compensation techniques, we can ensure that our embedded systems deliver precise, reliable, and accurate data, transforming raw sensor signals into meaningful insights for their intended purpose.